Hello everyone, my name is Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on redox reactions. Let's go ahead and get started with problem number 1. Problem number 1 says consider the following equation. Which species acts as an oxidizing agent? Now to answer this question, let's review some terms first. Remember that oxidation is the process where an element loses electrons and thereby increases its oxidation state. And reduction is the process where an element gains electrons and thereby decreases its oxidation state. Now, an oxidizing agent is the species that accepts electrons and gets reduced, and a reducing agent is the species that donates electrons and gets oxidized. To determine the oxidizing agent, the first thing that we're going to do is assign oxidation states to each element in the reactants and in the products. So some rules to keep in mind when we do that are the following. Rule number 1, the oxidation state of an element in its elemental form is equal to 0. Rule number 2, for monatomic ions, the oxidation state is equal to the charge of the ion. Rule number 3, hydrogen generally has an oxidation state of +1, except when it's bonded to metals in binary compounds. There, the oxidation state for that hydrogen is -1. Rule number 4 is that oxygen generally has an oxidation state of -2, except in peroxides where it is -1 or in compounds with fluorine. Rule number 5 is that the sum of oxidation states in a neutral compound must be 0, while in a polyatomic ion, it has to equal the ion's charge. Now let's go ahead and look at our equation and start assigning oxidation states. Let's start off with sodium. In its elemental form, sodium is going to have an oxidation state of 0. Next, let's look at ammonia. Hydrogen has an oxidation state of +1. Now, to balance the 3 hydrogens, which gives us a total of +3, nitrogen must have an oxidation state of -3. Then we can look at sodium nitride. Sodium, as an ion, has an oxidation state of +1. And there are 3 sodium atoms. Now, to balance this +3 charge, nitrogen must have an oxidation state of -3. Then last but not least, we can look at hydrogen gas. In its elemental form, this is going to have an oxidation state of 0. Okay, now let's look at the changes that are occurring. Let's look at sodium. Sodium goes from an oxidation state of 0 to +1. So that means that sodium is oxidized. If it is oxidized from 0 to +1, this makes it the reducing agent. Next, let's look at nitrogen. Nitrogen goes from an oxidation state of -3 to -3. There is no change in oxidation state for nitrogen. What about for hydrogen? Well, here, hydrogen has an oxidation state of +1, and then it changes to 0 because hydrogen here, as hydrogen gas, has an oxidation state of 0. So we're changing from +1 to 0. That means that the hydrogen is reduced from +1 to 0, making it the oxidizing agent. So the oxidizing agent here is the hydrogen in ammonia. And that makes the correct answer for problem number 1, answer choice C. Beautiful. Let's move on to problem 2. Problem 2 asks, how many electrons are involved in the following half reaction after it is balanced? We're looking at the reaction between dichromate and chromium 2 ion. Now, to start this off, we're not going to concern ourselves with the electrons. We're going to leave that at the end when our final step is to balance the charge. So we're going to look at this reaction without the electrons, and we're going to start by balancing atoms, starting off with chromium. Now, on the reactant side, we have our dichromate here, where we have 2 chromium atoms. To balance that on the product side, we're going to add a coefficient of 2 in front of the chromium 2 ion. Now, our chromium atom is balanced. The next atom we want to balance is our oxygen atoms. There are 7 oxygen atoms in the dichromate ion. So we're going to put a coefficient of 7 in front of water so that we have 7 oxygen atoms on the product side as well. Now, the number of oxygen atoms are equal to each other on both the reactant and product side. Now, our last and final step is to balance the hydrogen atoms. On the product side, we have 14 hydrogens. So to balance that, we're going to add a coefficient of 14 in front of our hydrogen ions. Now all of the atoms are balanced. Let's go ahead and calculate the charge on the reactant side and the product side so that we can determine how many electrons we need and on which side to balance the charge. Now on the left side, on the reactant side, we have a -2 charge from our dichromate ion, and we have a 14 plus charge from our hydrogen ions. 14 plus -2 gives us a total of +12 as our charge for the reactant side. What about our product side? In our product side, we only have a charge of 4 plus 2 from our 2 chromium 2 ions gives us a total of +4 charge. Now, the charges are not balanced. To ensure that the charge is balanced, we're going to have to add 8 electrons to the reactant side so that both sides have a charge that is equal to +4. So that means we need 8 electrons on the reactant side, which makes the correct answer B for problem 2. Awesome. Let's tackle problem 3. Problem 3 says lithium aluminum hydride is often used in laboratories because of its tendency to donate a hydride ion. Which of the following roles would lithium aluminum hydride likely play in a reaction? A says strong reducing agent only. B says strong oxidizing agent only. C says both a strong reducing agent and a strong oxidizing agent. And D says neither. Now, to determine the role that lithium aluminum hydride likely plays in a reaction, we need to understand the chemical properties and the common uses of lithium aluminum hydride in a laboratory setting. This is a powerful reducing agent that's commonly used in organic chemistry. Remember that a reducing agent is a substance that donates electrons to another substance in a redox reaction, thereby reducing the oxidation state of that substance. And the reducing power of lithium aluminum hydride, it stems from its ability to donate a hydride ion, which is a hydrogen atom with an extra electron. Now, as a general hint, strong reducing agents, they tend to have metals or hydrides, and strong oxidizing agents, they tend to have oxygen or similarly electronegative elements. So in short, lithium aluminum hydride acts as a strong reducing agent because it donates electrons in the form of hydride ions to other substances, facilitating their reduction. It is not known to be an oxidizing agent or to act as an oxidizing agent, as it does not accept electrons. Therefore, the correct answer is A. It is a strong reducing agent only. Let's move into problem 4. Problem 4 asks, what is the oxidation number of chlorine in sodium hypochlorite? Now, to start this, let's once again review our rules for assigning oxidation numbers. Rule number 1 is that the oxidation state of an element in its elemental form is 0. Rule number 2, for monatomic ions, the oxidation state is equal to the charge of the ion. Rule number 3, hydrogen generally has an oxidation state of +1, except when it is bonded to metals in binary compounds. There it will have an oxidation state of -1. Rule number 4 is that oxygen generally has an oxidation state of -2, except in peroxides where it is -1 or in compounds with fluorine. And then the last rule is that the sum of oxidation states in a neutral compound must be 0, while in a polyatomic ion, it must equal the ion's charge. So now let's take a look at our compound. Here, sodium is an alkyl metal. It's going to have an oxidation number of +1, and oxygen typically has an oxidation number of -2. Now, this is a neutral compound, which means that the chlorine atom must carry a +1 oxidation state in order to balance the overall charge of 0. Because +1 plus 1 minus 2 gives us a sum of 0, which is what we're looking for since sodium hypochlorite is a neutral compound. The correct answer for problem 4 is C. Let's move on to problem 5. Problem 5 says the following electronic configurations represent elements in their neutral form. Which element is the strongest oxidizing agent? To answer this question, we should keep in mind that an oxidizing agent is a substance that gains electrons in a chemical reaction and gets reduced. Strong oxidizing agents, they typically have high electronegativity and a strong tendency to accept electrons. Now, considering we're given the electronic configuration for elements in their neutral form, what we can do is identify the atoms and then discuss them one by one. So for answer choice A, this is the electronic configuration for calcium. Calcium is an alkali earth metal. It tends to lose electrons rather than gain them, making it a poor oxidizing agent. Also, to keep in mind, it has a full 4s orbital, meaning that it can only gain an electron if it gains an entire subshell. So answer choice A is not what we're looking for. Answer choice B gives us the electronic configuration for manganese. Now, manganese can exhibit various oxidation states, but in its neutral state, it is not a strong oxidizing agent as the other options. Also, it is stable with a half-full 3d orbital, so it's unlikely to pick up electrons unless it can gain about 5 more. So this is not the answer we're looking for. Answer choice C gives us the electronic configuration for gallium. This is a metal and it tends to lose electrons to form cations, making it a poor oxidizing agent. Also, it has a single electron in the outer shell, which is more likely lost upon ionization. So again, this is not what we're looking for. Answer choice D gives us the electronic configuration for bromine. Bromine as a halogen has a high electronegativity and a strong tendency to gain electrons. Halogens are actually well known for being strong oxidizing agents. In other words, it would fill up its 4p orbital by gaining 1 electron, so it is easily reduced and it is a strong oxidizing agent. This is what we're looking for, and so the correct answer for problem 5 is answer choice D. Let's move on to problem 6. Problem 6 asks, which of the following is the correct net ionic reaction for the reaction of copper with silver 1 nitrate? To determine the correct net ionic reaction, we need to follow our 3 main steps. First, we write the molecular equation with all of the reactants and all of the products in their undissociated form. Next, we can write the total ionic equation, noting that all of the soluble compounds should be written in their dissociated form. Then last, by removing the spectator ions, we get the net ionic equation. So let's do that for this reaction. First, we're going to start with the balanced molecular equation for the reaction. We have copper reacts with silver nitrate to form copper 2 nitrate and silver. So here we have the balanced molecular equation. Next, we want to write the total ionic equation by dissociating all of the strong electrolytes, all of the soluble salts, into their constituent ions. This gives us the following equation. In this total ionic equation, what we notice is that the nitrate ions appear on both sides of the equation. They do not participate in the actual chemical reaction. These are known as spectator ions. We can remove the spectator ions to simplify the equation, really just focusing on the species that undergo the chemical change. And after removing the spectator ions, we are left with the net ionic equation. This is our net ionic equation, and it matches answer choice D. So the correct answer for problem 6 is D. Let's go ahead and move into problem 7 now. Problem 7 says one way to test for the presence of iron in solution is by adding potassium thiocyanate to the solution. The product when this reagent reacts with iron is iron thiocyanate, which creates a dark red color in solution via the following net ionic equation. How many grams of iron sulfate would be needed to produce 2 moles of iron thiocyanate? Now, what we're shown is a net ionic equation. If 2 moles of iron thiocyanate are created, then we're going to need 2 moles of iron because there is a 1-to-1 mole ratio between these two species. Now, iron sulfate has the formula Fe2SO4 because the sulfate has a charge of -2 and iron has a charge of +3. We get this based off of the net ionic equation we're given. Therefore, 1 mole of iron sulfate is needed to make 2 moles of iron for the reaction. And if we have 2 moles of iron, then we can make 2 moles of iron thiocyanate. So what we need to figure out is the molar mass of iron sulfate. That is the grams of iron sulfate that we're going to need to produce 2 moles of iron thiocyanate. To figure out the molar mass of iron sulfate, we just need to figure out how many of each atoms we have and what the molar mass of each atom is. So we have 2 iron atoms. Iron has a molar mass of 55 grams per mole. We have 3 sulfate atoms. Sulfate has a molar mass of 32 grams per mole. And we have 12 oxygen atoms. Oxygen has a molar mass of 16 grams per mole. 2 times 55 is 110. 3 times 32 is 96. And 12 times 16 is 192. If we go ahead and add this up, we should get approximately 400 grams per mole. Now we know that we just need 1 mole of iron sulfate to get 2 moles of iron. With 2 moles of iron, we can make 2 moles of iron thiocyanate. So the answer here is going to be answer choice C. 7 is C. Let's move on to problem 8. Problem 8 says, during the assigning of oxidation numbers, which of the following elements would most likely be determined last? So when we're assigning oxidation numbers, we usually start with elements of known oxidation state first, and then we determine the oxidation state of other elements by deduction. Let's work through each of these answer choices. A says argon. Argon is a noble gas. It typically does not form compounds. So when it's present in a reaction, it's usually going to have an oxidation state of 0 because it's going to exist in its elemental form. B says fluorine. Fluorine can have an oxidation state of 0 when it's on its own or -1 in a compound. This can be usually determined first, so it's not what we're looking for. C says strontium. Strontium is an alkaline earth metal with a fixed oxidation state of +2 in compounds. This makes it straightforward to assign its oxidation number early in the process. And again, this is not what we're looking for. D says iridium. This can exhibit multiple oxidation states from -3 to +8. And so due to its variable oxidation states, the assignment of its oxidation number often depends on the oxidation states of the other elements in the compound. Therefore, it's usually determined last. And that makes the correct answer for problem 8, answer choice D. Let's move on to problem 9. Problem 9 says, as methanol is converted to methanal and then methanoic acid, the oxidation number of the carbon blank. Does it increase? Does it decrease? Does it increase then decrease? Or does it decrease then increase? In order to answer this problem, we need to figure out the oxidation state of carbon in each of these compounds. Let's go ahead and start with methanol. Now, methanol is a neutral compound, so the sum of the oxidation states must add up to 0. Keeping that in mind, methanol has a molecular formula of CH3OH. Hydrogen here has an oxidation state of +1, and there's a total of 4 hydrogen atoms, so +4. Oxygen here has an oxidation state of -2. There's only 1 oxygen atom. In order for the oxidation states to sum up to 0 then, carbon must have an oxidation state of -2. So in methanol, carbon has an oxidation state of -2. What about methanal? This is going to have a molecular formula of HCHO. Again here, hydrogen has an oxidation state of +1, and there's a total of 2 hydrogen atoms, so +2. Oxygen has an oxidation state of -2, and considering that methanol is a neutral compound, that means that the sum of the oxidation states must add up to 0. We have +2 from the hydrogen atoms, -2 from the oxygen atom. This already sums up to 0. To keep it that way, carbon must have an oxidation state of 0. Then the last compound we're going to look at is methanoic acid. Again, this is a neutral compound, so the sum of the oxidation states must add up to 0. The molecular formula here is HCOOH. The hydrogen has a oxidation state of +1, and there's 2 hydrogen atoms here, so +2 total. Oxygen has an oxidation state of -2, and there are 2 oxygen atoms, so we have a total of -4. +2 minus 4 so far gives us -2. In order to ensure that the sum of the oxidation numbers in methanoic acid is 0, carbon must have an oxidation number of +2. That way we have +2 plus 2, that's a total of 4, minus 4, that gives us a total of 0. So then as we move from methanol to methanal to methanoic acid, we are going from an oxidation number of -2 to 0 to +2. And so the oxidation number of carbon is increasing from -2 to 0 and increasing again from 0 to +2. And that makes the correct answer for problem 9, A. The oxidation number of the carbon increases going from methanol to methanal to methanoic acid. Let's move on to problem 10. Problem 10 asks, in the compound potassium dihydrogen phosphate, which element has the highest oxidation number? Now, something that's important to note is that this is a neutral compound, which means that the sum of all the oxidation numbers must sum up to 0. Keeping that in mind, let's get started. Potassium here is an alkali metal, and in compounds, it always has an oxidation number of +1. Hydrogen also typically has an oxidation number of +1 when it's bonded to non-metals, and there are 2 hydrogen atoms total. Oxygen has an oxidation number of -2, and we have a total of 4 oxygen atoms. So this gives us -8. Now, the oxidation number of phosphorus will be determined by ensuring that the sum of the oxidation numbers in the compound equals the overall charge of the compound, which is neutral. That means 0. Right now we have 3 minus 8. That gives us a sum of minus 5. To ensure that we get a sum of 0, the oxidation number of phosphorus must be plus 5. This makes the correct answer for problem 10, answer choice C. Phosphorus has the highest oxidation number. Now, moving on to problem 11. Problem 11 says if a certain metal has multiple oxidation states, its acidity as an oxide generally increases as the oxidation state increases. Therefore, which of the following tungsten compounds is likely to be the strongest acid? We're looking at which tungsten compound has a tungsten atom with the highest oxidation number. So let's look at answer choice A. Here we have tungsten 4 oxide. We have an oxygen atom which has an oxidation state of -2, and we have a total of 2 oxygen atoms, so this gives us -4. Since this is a neutral compound, to ensure that the sum of the oxidation states equals 0, tungsten must have an oxidation state of +4. Then for answer choice B, we have tungsten 6 oxide. Here we have oxygen again with a -2 oxidation number. We have 3 total oxygen atoms. This gives us -6. Again, this is a neutral compound. To ensure that the sum of the oxidation numbers equals 0, tungsten must have an oxidation number of +6 here. For answer choice C, again, oxygen with a -2 oxidation number, and there is a total of 3 oxygen atoms. We get -6. What is the oxidation number of tungsten to ensure that the sum equals 0, considering we have 2 tungsten atoms? In this case, it will have a +3 oxidation state. Then for our last and final answer choice, again, oxygen -2 oxidation number, and then we have 5 oxygen atoms. This gives us -10. This is a neutral compound. To ensure that the sum of the oxidation numbers equals 0, tungsten has to have an oxidation number of +5 because we have 2 tungsten atoms. This gives us -10 plus 10, that equals 0. So now looking at these answer choices, the compound that has a tungsten atom with the highest oxidation number is going to be answer choice B. This is tungsten 6 oxide. So 11 is B. Beautiful. Let's move on to problem 12. Problem 12 says, consider the following steps in the reaction between oxalic acid and chlorine. Which of these steps occurring in aqueous solution is an example of a disproportionation reaction? Now, a disproportionation reaction is a type of redox reaction in which a single substance is both oxidized and reduced, forming at least 2 different products. Let's go ahead and look at step 1 first. Here we have chlorine, and chlorine is converted to both hypochlorous acid and chloride ions. Chlorine here has an oxidation state of 0. In hypochlorous acid, it has an oxidation state of +1. And in the chloride ion, it has an oxidation state of -1. So here, chlorine is both oxidized, going from 0 to +1, and reduced, going from 0 to -1. And this makes this reaction a disproportionation reaction. What about step 2? Here we see an acid dissociation reaction where oxalic acid dissociates into hydrogen ion and hydrogen oxalate ions. Now here, there is no change in oxidation state, so it is not even a redox reaction, let alone a disproportionation reaction. So step 2 is not what we're looking for. What about step 3? In this reaction, we have hypochlorous acid and hydrogen oxalate ions reacting together. They give us water, chloride ions, and carbon dioxide. Now, this reaction is going to involve the reduction of hypochlorous acid to chloride, because here we're going from +1 to -1, so it is reduced. And then we see the oxidation of oxalate ions to carbon dioxide. So since the same species is not both oxidized and reduced, This is not a disproportionation reaction. That means that the only step that represents a disproportionation reaction is step 1 because chlorine undergoes both oxidation and reduction. Therefore, the correct answer to problem 12 is A. Let's move on to problem 13. Problem 13 says potentiometry in an oxidation reduction titration is analogous to performing an acid-base titration with a blank: acidic indicator, basic indicator, pH meter, or an oxidizing agent. Now, in an acid-base titration, the pH of the solution is monitored to determine the endpoint of the titration. This is typically done using a pH meter or an indicator that changes color at a specific pH value. Similarly, in an oxidation reduction titration, the potential or the voltage of the solution is monitored to determine the end point. This is where potentiometry comes into play. Here, this involves measuring the electrical potential or voltage of a solution to monitor the progress of a redox reaction. It is used in redox titrations to determine the equivalence point, which is analogous to how a pH meter is used in acid-base titrations. So a pH meter, is used to detect the endpoint and the equivalence point of a titration by indicating when the pH changes significantly. So in the context of this question, potentiometry in a redox titration serves a similar role to a pH meter in an acid-base titration. Both methods involve monitoring a specific property to determine when the reaction has reached its equivalence point and its endpoint. So the correct answer here is going to be C. Let's move on to problem 14. Problem 14 says, after balancing the following oxidation reduction reaction, what is the sum of the stoichiometric coefficients of all of the reactants and products? In order to get the sum of the stoichiometric coefficients of all the reactants and products, we need to balance this redox reaction. And to do that, we're going to use our half reaction method. To be able to get our oxidation half reaction and our reduction half reaction, we need to look at this reaction and decide what is being oxidized and what is being reduced. So our first step here is going to be to assign oxidation numbers to all of our atoms. Starting off here, each sulfur atom in elemental sulfur has an oxidation number of 0. Then we can look at our nitrate ion. It has a charge of -1. So that means the sum of the oxidation numbers needs to be equal to -1. Here we have oxygen. Oxygen has an oxidation number of -1. And there are a total of 3 oxygen atoms. This gives us -6. In order for our sum to be equal to -1, the oxidation state of nitrogen needs to be +5. -6 plus 5 gives us -1. That is exactly matching our charge for this polyatomic ion. Next, we're going to look at our sulfite ion. Here, this has a charge of 2-, so the sum of the oxidation states need to be equal to -2. Again, here we have oxygen with a -2 oxidation number, and there are 3 oxygen atoms, so we have -6. In order for the sum to be equal to -2, sulfur needs to have an oxidation state of +4. Then last but not least, we can look at nitrogen monoxide. Oxygen here is going to have an oxidation state of -2, so nitrogen will have an oxidation number of +2. Now we can look a little bit more in depth and decide what is being oxidized and what is being reduced. Sulfur here goes from 0 to +4. Sulfur is oxidized. Then we can look at nitrogen. Nitrogen is going from +5 to +2. Nitrogen is being reduced. So with that information, we can go ahead and write our oxidation half reaction and our reduction half reaction. Then the goal is to balance each half reaction individually and then combine them together to get the overall reaction. Let's start off with balancing our oxidation half reaction. Here on the reactant side, we have 8 sulfur atoms. To balance this with the product side, we're going to add a coefficient of 8 right here. Now, on the product side, we have 24 oxygen atoms. In order to balance that with the reactant side, we're going to go ahead and add 24 water molecules. Now, the sulfur atoms are balanced and the oxygen atoms are balanced, but the hydrogen atoms are not. On the reactant side, we have a total of 48 hydrogen atoms. So to balance that on the product side, we're going to add 48 hydrogen ions. Now all the atoms are balanced, but our final step is to go ahead and balance the charge. On the reactant side, we have a charge of 0. And on the product side, we have a charge of minus 16 plus 48. This gives us a charge of positive 32. To get this positive 32 charge to be equal to 0, like it is on the reactant side, we're going to add 32 electrons. So now we have a balanced oxidation half reaction. Our next step is to do the same for our reduction half reaction. Here on both the reactant and the product side, we have one nitrogen atom. Now let's do the oxygen. On the reactant side, we have 3 oxygen atoms. On the product side, we only have 1 oxygen atom. To balance it, we're going to add 2 water molecules. Now there's 3 oxygen atoms on both sides. The next thing to balance is the hydrogen atoms. We have 4 on the product side, so we're going to go ahead and add 4 hydrogen ions to the reactant side to balance that. Now all of the atoms are balanced. We need to make sure that the charge is balanced. On the reactant side, we have minus 1 plus 4. We have a total charge of plus 3 on the reactant side and 0 on the product side. To get the reactant side to be equal to the product side, we just need to add 3 electrons to the reactant side. Now we have a balanced reduction half reaction. Both of our half reactions are now balanced. The next thing we want to do is add them together, but in order for us to add them together, we need to have an equal number of electrons in both of these reactions. Now here on the oxidation half reaction, we have 32 electrons, and here in our reduction half reaction, we have 3. The common number here is going to be 96, which means that we need to multiply our oxidation half reaction by 3, and we need to multiply our reduction half reaction by 32. So when we do this, we can go ahead and begin to modify our value. So I'm going to erase all of our coefficients and modify them appropriately now that we're multiplying by a different coefficient. So let's go ahead and do that, starting off with our oxidation half reaction. Now we have 72 water molecules. We have 3 of these S8 molecules. We have 24 sulfite molecules, 144 hydrogen ions, and 96 electrons. That is our oxidation half reaction. What about our reduction half reaction? Now we have 32 nitrate ions, 128 hydrogen ions, 96 electrons, 32 of these nitrogen monoxide molecules, and we have 64 water molecules. Now we can go ahead and add together these 2 reactions, noting that the electrons are going to cancel out. What we're going to get now is the following equation. We now have 3S8 plus 32 nitrate ions plus 8 water. All right, and that gives us in our product side 24 sulfite. All right, sulfite ions, 2 minus, plus 32 nitrogen monoxides plus 16 hydrogen ions. All right, and note that our number of hydrogen ions and for water, they have been modified because we made sure to go ahead and cancel out similar numbers of water molecules from both sides. So this gets us the following overall reaction. Now all we have to do is sum up the coefficients. So here we have 3 plus 32 plus 8 plus 24 plus 32 plus 16. This is going to give us a total of 115, which makes the correct answer for problem 14 answer choice D. Beautiful. Now we can move into our last and final problem for this video. Problem 15 says an assay is performed to determine the gold content in a supply of crushed ore. One method for pulling gold out of ore is to react it in a concentrated cyanide solution. The equation is provided below. Now, an indicator is used during this reaction, and approximately 100 milliliter of a 2 molar sodium cyanide solution is used to reach the endpoint. How many moles of gold are present in the crushed ore? The first step that we want to do is go ahead and balance the chemical equation. I went ahead and did this for us since we've had plenty of practice balancing chemical equations, but go ahead and check for yourself. Now that we have the balanced chemical equation, the second thing we want to do is determine the number of moles of sodium cyanide that's used in this reaction. We can determine this because we know the volume and the molarity, so we can easily solve for the moles. What we're going to have to do is multiply the volume, which we're going to convert to liters, 0.1 liters, and we're going to multiply this by the molarity, which is 2 moles per liter. Notice that the units of liter cancel out, and what we're going to be left with in terms of units is mole. 0.1 times 2 is equal to 0.2 moles of sodium cyanide. Now we're going to use this amount to do a conversion to number of moles of gold. And the way we're going to do that is by taking advantage of our balanced chemical equation and by using mole-to-mole ratios. So if we have 0.2 moles of sodium cyanide, we can use a mole-to-mole ratio between sodium cyanide and gold. For 8 moles of sodium cyanide, we have 4 moles of gold. And what we're going to get here is 0.8 divided by 8, and this is going to be equal to 0.1 moles of gold that is in our crushed ore. And that makes the correct answer, answer choice C. And that's how we solve problem 15. And with that, we've completed our practice problem set for our redox lecture. Please let me know if you have any questions, comments, concerns down below. I really hope that this was helpful. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.